Hey class, in this recording, we're going to be focusing on cartilage, bone, and blood. As we look at cartilage, it's a stiff connective tissue. Also, it's going to have a little bit of flexibility to it, and there's different kinds of cartilages that have varying degrees of stiffness and flexibility to them. So wherever we find something in our body that's fairly rigid but flexible, like our ears, our nose, or larynx, aka our Adam's apple, is what most people refer to that as, we're going to find a lot of cartilage. And within cartilage, there's a cell type called a chondroblast. Blast means to build. It's a construction cell, and it's going to build cartilage. So these are the cells that make the extracellular matrix of the cartilage. And when they're done making that extracellular matrix, they are completely trapped or encapsulated in cartilage extracellular matrix, and the cell morphs or transitions into a chondrocyte, being a cell that is going to sit in a cavity of the cartilage. And we call that cavity or space the lacuna. We find that we also are going to have wrapped around our cartilage tissue something known as the perichondrium. And the perichondrium is in a membrane or a sheath of dense irregular connective tissues. And it's going to surround our elastic and a lot of our hyaline cartilages. And it just serves to help give us a definitive ending point of that tissue. The perichondrium is going to have chondroblasts in reserve, and we use those chondroblasts to constantly regenerate and grow little bits of cartilage throughout our life cycle, throughout our lifespans. Something that's notable about cartilage is that it is avascular. It has almost no blood vessels present in it. This means that the diffusion of nutrients is the only way we can bring stuff in and out. And because there's a high density to the extracellular matrix, there's a very low rate of diffusion with getting nutrients in and getting waste removed. Because there's a low rate of nutrient delivery and waste removal, cartilage tends to heal slowly. To speed up the rate of nutrient delivery and waste removal, you need to have a little bit of physical activity. You need to compress and relax that cartilage again and again. It's kind of like having a sponge suck up water and then squeezing the water out, and suck up water and then squeezing that water out. And that process is going to help actually heal the cartilage. Very mild or gentle physical activity, going for a walk, going gardening, maybe playing tag with your kids, is going to increase the rate of cartilage regeneration. Cartilage has a lot of glucosaminoGlycans or GAGs in it. And those glucosaminoGlycans are molecular sponges that will suck up water. And cartilage is also going to have a lot of collagen fibers to give it some structural integrity. There are different kinds of collagen fibers that will be present in either hyaline, fibro, or elastic cartilages. So let's dive into it and look at hyaline cartilage. In my mind, I lovingly refer to hyaline cartilage as fish eye soup. It just looks like a bunch of fish eyeballs floating around in some soup. And the eyeball itself is the chondrocyte. Then we have the clear cytoplasm and the dark purple nuclei. And then the extracellular matrix of hyaline cartilage is kind of usually going to be stained kind of a uniform purple or light pink or light blue color. And that's the soupy part of the soup. We find that we have very clear extracellular matrix because there's a kind of collagen fiber that's incredibly fine and small within hyaline cartilage. We use hyaline cartilage to reduce friction in joints, so to ease joint movement. We use hyaline cartilage to hold our airways open. We also are going to use it as a precursor for bones. So when we have bone formation, a lot of times that bone starts out as hyaline cartilage, and then the hyaline cartilage gets converted into bone. We find a lot of hyaline cartilage in our rib cage, our trachea, our larynx, the undeveloped fetal skeleton, and in any freely movable joint. The articular cartilage is a form of hyaline cartilage. As we look at elastic cartilage, this kind of cartilage is going to have lots of elastic fibers in its extracellular matrix, in addition to those very fine collagen fibers. So when we look at elastic cartilage, these thin black lines that you see in the extracellular matrix are typically just elastic fibers. There's also going to be a lot of perichondrium surrounding the elastic cartilage to help it to maintain its initial shape. So we have something that's very flexible, but at the same time supportive. So if we look at our external ear, it has a lot of elastic cartilage. I'm wiggling mine right now. Hopefully you can reach up and wiggle your external ear right now. Let's leave our epiglottis alone. Now, I don't want to wiggle my epiglottis down in the back of my throat just because that's really uncomfortable. But the epiglottis is another structure in the body known for having a lot of elastic cartilage present in it. Now, as we look at fibrocartilage, it has large, coarse bundles of collagen fibers. So as we look at these collagen fibers, you can see broad bands of collagen fibers within our fibrocartilage. And this allows for our fibrocartilage to be really tough. This is our shock absorber, impact absorbing cartilage. And we're going to have fibrocartilage in between all the vertebrae of our body. We have fibrocartilage in our knees as within the menisci, and we also have a lot of fibrocartilage at our pubic symphysis, in between the two pubic bones of our body, that allows for some flexion of our pelvic girdle. As we look at bone tissue, there are two kinds of bone tissue that we typically like to emphasize. We have spongy bone tissue and compact bone tissue. These are all just generically referred to as osseous tissues or bone tissues because they have a calcified extracellular matrix. A spongy bone is going to have a very porous appearance. It's going to look like a sponge. And the individual fibers of the spongy bone are referred to as trabeculae. I'm going to jump ahead a slide here. Never mind, I actually don't have a photomicrograph of that. Thankfully, we do cover spongy bone in lab, and you can see what it looks like during lab. Our spongy bone is always going to be surrounded by a sheath of compact bone. And we find that spongy bone is typically going to be filling large cavities within our bones. So if you have a bone with a lot of girth to it, that bone is probably going to have a bunch of spongy bone on the inside so that we can still fill it up, have some structural support and integrity, but at the same time not have a lot of unnecessary mass in our bodies. And then we have compact bone. It's very dense. Sometimes it's just referred to as dense bone, and it doesn't have any visible space in its extracellular matrix. It is a very complex arrangement of concentric circular structures known as osteons. And we find that this compact bone is the most common kind of bone tissue in our bodies. So let's jump ahead here and look at some compact bone in a photomicrograph. You can see how we have these dark central canals or Halbertian canals, these dark bullseyes. And then there's concentric circles going around these structures. These compact bone tissues are going to have lots of these concentric circle structures, which are referred to as osteons. And in the very center of our osteons, we have something known as the central canal. Each ring of that osteon is called a lamella because it looks like it's laminated with multiple onion-like layers going around the central canal. And the osteons typically are going to run lengthwise with long bones, or they're going to be longitudinally oriented with bone. Now, as we look at one osteon in detail, we have that central canal, aka the Halbertian canal, in the center. We're also going to have a bunch of osteocytes, which are represented by these dark slits. This dark spot that I just drew an arrow to is a twofer. It represents a cell. It also represents a space. We call the cell an osteocyte. We call the space a lacuna. And then we have tiny little branches coming away from the osteocyte. Those tiny little branches are going to be referred to as canaliculi. And they allow for extensions of the osteocyte to penetrate the compact bone tissue and serve as pressure sensors. So that with one osteocyte is under a lot of physical tension or pressure, it can contact other osteocytes. It can monitor tension on bones and adjust bone density if we increase pressure over time, or reduce bone density if we reduce bone tension and pressure over time. And then finally, around the outer layer of our long bone, we have something known as the periosteum. And that periosteum is, if we look at this word peri, that means perimeter. Oste meaning bone. A periosteum is going to be just a layer of tough fibrous tissue around the outer perimeter of our bones, kind of like the perichondroitum, which is that tough membrane around the outside of cartilage tissues. We also have blood, and blood and bone are kind of the odd ducks out. Bone is a solid at room temperature. It is the only tissue in the body that is rigid and stiff and not pliable. And then blood is an odd duck out because it is one of two tissues in the body, arguably two tissues, that is a liquid at room temperature. Some people like to make the case that lymphatic fluid is also a tissue as well. I'm personally kind of on the fence with that one, but blood is absolutely a tissue and is absolutely a fluid. And as we look at blood, plasma of the blood is going to be the ground substance of that tissue. And it's going to have almost no extracellular fibers or fibers within its extracellular matrix. And there are three kinds of cells and cell fragments within our blood that we typically emphasize. We have the red blood cells, known as the erythrocytes, white blood cells, known as leukocytes, and thrombocytes, commonly referred to as platelets. And a thrombocyte is actually a fragment of a larger cell known as a megakaryocyte. And as we look at the leukocytes that we have in our bodies are referred to as neutrophils, lymphocytes, monocytes, eosinophils, and basophils. Those are the 5 broad categories of leukocytes. That's all we have for this recording on cartilage, bone, and blood. If you have any questions about these connective tissues, please feel free to post them in the class discussion board or to shoot me an email. And as always, class, happy studies.